Today we are going to learn about DenseNet. So, while in the last few ones we had gone down very much deeper. So, we started with Google Nets and then eventually we went on to the newer kind of ones where you could have some sort of connections from a previous layer to the next layer. So, one of them was called as Resql network which or ResNet, and that is what we had done in the last one. So, the whole idea behind ResNet or residual network was that you had to take down the part of the input and then combine it with whatever is coming out of the convolution layer. Now, as an essence, what the intermediate convolution layers over there are going to learn down is a difference between the between whatever goes into the input and what comes out of the output, and this is what's also termed as a residual learning problem. Now, this is one part of it where you are just arithmetically adding down your inputs to your outputs and then creating your resultant output from there. Now, on the other side of it is what's called as a dense residual connection, and that was a paper from CVPR 2017. And what happened out in a dense residual connection was more of in a way that you get your inputs, then you start concatenating your inputs to the subsequent layers, and then so what essentially happens is that you are not going to arithmetically add, but you preserve all the features by appending them onto the feature channels which comes as the output, and then subsequently it keeps on passing through the whole network over there. Now, the advantage which you gain in dense residual network over coming down from a ResNet was that you could reduce down significantly the total number of weights or the total number of parameters over there. And one of the reasons why you could significantly reduce down the number of parameters was that you could use much lesser number of channels for doing this whole purpose over here. Now, being able to reduce down the total number of channels over there is what plays a significant role in terms of bringing down the total model complexity while improving down the total accuracy of the model over there. Now, having said that, while we have learned down on the theory part of it, today let us look into a dense residual connection network. So, we are going to do down it with DenseNet. Now, as going down with any of the conventional ones which we have done till now. So, we have our first part of the header which is quite straightforward and simple as we keep on taking it up. Now, once this part of the header is completely done, the next is that we employ it on a CFAR problem. Now, over here the data which we are going to take down is of the size of 224 cross 224 pixels and 3 channels over there. Now, we are able to handle down 32 batch sizes. Now, this is a really large batch size as if you look down as comparison to a VGGNet where your batch size was much smaller. Now, one of the reasons that you are able to handle down a larger batch size over here is because your total number of parameters actually are much lesser, and in essence that when you are reducing the total number of parameters over there, the intermediate memory consumed internally over there is also reduced down in some sense. Now, what we are doing is instead of looking down into ImageNet kind of a problem which was a 1000 class classification problem, we are just making use of 10 class classifications over here. So, we have the CFAR 10 which is a 10 class classification problem. We take the train and the test over here, and then we are just rescaling out all the images over there to 224 cross 224, and then eventually we keep on doing with that one. Now, having said that, the next part is quite simple, which is just to look down and onto the size of the images, and we just have 50,000 images for training and 10,000 images for testing, and that is how it simply goes on. Okay. Now, for the architecture part of it, we use the same old concept from our earlier concept of using data loader, using from our torch vision library our models. So, these were all pre-trained models or predefined models which were present over there, and today we are going to make use of DenseNet 121 in order to solve it out. So, I just do a pointer call from my models library over there, and this is what is used for doing a pointer call onto a DenseNet 121. Okay. Now, let us look into the network over there. This was a plain simple way of printing down to the network as we had done in the earlier cases as well. Now, if you look down, so you have your first part which is a 2D convolution of 3 cross 3 kernel sizes, and you have 64 kernels coming out of it. You have a 3 cross 3 kernel size over there. There are 3 channels, 7 cross 7 kernels over here for convolution. You have 3 channels as your input channels, 64 channels as your output channels which comes out. And now, what we also do is we try to do a stride, and the stride over here is a stride of 2. Okay. Now we do pad down with 3 zeros on either sides over there, and one of the major reasons of padding it down with 3 zeros was such that your size of the image which goes, your spatial span of the image which goes as the input and which comes out as the output is quite on the similar size, and since it is a stride of 2, so it's everything is divided by 2. So your input is a 224 cross 224, whereas your output over there is 112 cross 112 which comes out. Okay. Now following that we have a batch normalization, and then you have your ReLU, and then you have a max pool. Now this is what constitutes the first layer of convolution. Now in the subsequent one is when your dense layers actually start coming into play. Then your first dense layer over there you have a 2D convolution which has a size of 1 cross 1, and it takes in 64 channels which were the output from the 64 channels on the earlier layer, and then it generates an output of 128 channels over there. Okay. Now this does it with a stride of 1 comma 1, which necessarily mandates that your size of the image does not reduce. So your input was of a spatial size of 112 cross 112, your output is also 112 cross 112. Okay. Now from there you get into this the next convolution layer, which is the third over there. Now you put down 128 layers over here, and you generate 32 layers over there. Now the kernel sizes over here are very different. These are now 3 cross 3 kernels with a stride of 1 comma 1. So that means that your total spatial span has in no way decreased. The spatial span is still going to remain the same. Now this is what happens down with one dense block over here, and then you enter the next dense block, and so on and so forth. You keep on going down. Now within each dense block, as it keeps on going, that you keep on appending your layers subsequently from the previous layers to the next one. Okay. Now with that being done down, what you come down at the end is, just wait for it. Yeah, so at the end over there is finally when you get down 1024 neurons at that the final linearized out part, and then as we have been doing with the earlier cases, was connect down these 1024 onto 1000 neurons for your classification nodes over there, and then this is your classification which comes out. Okay. Now that goes out good. Now over here we just do a calculation on the total number of parameters. So this was again in the same way as we had repeated with earlier examples of setting it down. So we just look down at the number of tunable parameters or the kernel sizes per layer. So wherever you have 2D kernels or so wherever you have convolution kernels present over there, this is what comes down, and then these weights over here are something which is associated with the biases as well as with the extra additions which keep on going. So whether you are going to replicate all the models over there on the dense convolution part over there. So that's what keeps on going, and if you take a sum total over all of these, then you would be finding out that the total number of parameters over there is about 7.9 million or close to 8 million. So that's 7. So this is 7,978,856 parameters in total which you have over here. Okay. Now given the fact that this was just 121 layers, so if you are trying to compare it with one of your residual connections over there, then the total number of parameters which you will be finding down in your residual connections is something in the same is almost twice as that of with a dense residual connection over here. Now if you just compare full residual connections with your dense residual connections over here, then you would find out that you have almost half the number of parameters, and that's what we had seen down in the earlier lecture slide as well. So with just using half the total number of parameters as you would have otherwise had, you can actually come down to the same accuracy level over here. Okay. Now comes down the modification which we need to do. So the whole point was that in the earlier case we were doing it with an ImageNet kind of a problem where you had to classify it to 1000 classes. Now I cannot have a mechanism of classifying it to 1000 classes, so we will have to bring it down because here it is just 10 classes to which it has to be classified. So let us just classify it down to 10 number of classes, and that is the next addition which we do. And for that what we do is net.classified is the pointer which is present over there. So we just put down this rest of the pointer onto this one, which connects down 1024 nodes onto just 10 nodes over there. So this does and then closes our total network for the classification for a 10 class problem. Okay. Now doing that, what we start by doing is, now that we have our modified new network which can work out actually on CFAR 10. So we start by copying down the weights. Now once we copy down all the weights, we just keep it over there, and then I just check out if GPU is available for my system to work on. Now if GPU is available, then that's well and good, and we can keep on proceeding over there. Now the next part which comes down is what is the actual loss function which we are doing, and again following down with what we had done in the earlier cases was if we have a classification problem, we just stick down to using negative log likelihood criteria. So we are still taking down the same loss function over here. So this is NLL loss function. Okay. Now for optimizer, based on our previous experiences and what we had done in the earlier class as well, so we are just taking down to Adam, which is one of the best optimizers to use over here. So we stick down to Adam, and then we are just making use of Adam for our optimization purposes over here. Now comes the training part of the network. Okay. Now within this training part of the network, what I am going to stick down is that I am just going to take down 10 iterations over there, no more, not more than 10 iterations, and just run it simple. Now since the total number of parameters over here is much lesser as well, so that would assist me in a big way, and because of lesser number of parameters, my total epochs will be taking lesser amount of time over there. Now what we need to get down into it. Now the first part of it is which looks into per epoch based losses is quite the same. The next is to get down into our batches, and that is where we make use of the train loader over here to do it. Now what I do is actually to find out if GPU is available, then I just convert down my available inputs and my network onto a GPU. If GPU is not available, then I am just not going to convert that over there. Now once that part is done, the next is to find out at my loss. So this loss is what is computed down using my criterion function per batch. Now once that is computed and I have my loss available, so I do a back propagation, and the gradient computation is what is done with loss dot backward over there, and then I just run down the optimizer step over there. Now the point of running down this step is just to run down the optimizer, and within each batch we are going to do. Now what you need to keep in mind is that this network is quite unlike GoogleNet, where the issue was to get down auxiliary losses as well. But here, since we do not have any of these auxiliary classification arms coming down, so we do not have an issue of auxiliary losses computed. So it is just the loss which is computed at the end of it. Now the other fact, which was like if there is a loss which is computed at the terminal part of it, then does that loss somewhat propagate back and get down to the earlier part of it? Yes, that is also pretty much what it does, because you have your dense residual connection. So there is always one part of the tap which comes down from the first part of the network and goes to the complete end, and as well as taps into all of these middle. So what happens during a back propagation is that each of these paths themselves back propagate all the gradients back to the start of the network, and that is how the whole weights and everything are updated over there. Okay. Now from there we come down to our running loss per epoch, and then you just sum it up and get down an average value of it. So this was plain straight as we had done in the earlier examples as well, and there wasn't anything new to do over here. Now the next part is to look into our testing data. Now in the test data also I just check out if GPU is available, then I just work it out on the GPU over there, otherwise I just leave it out on the CPU and then find out my loss, and then I get down whatever my loss comes down. Okay. Now with that, finally we come to a plot over here, and this part of the code is again plain simple as we had done in the earlier cases as well. So let us look into what it takes down. Now we have just shifted over to a different machine and a different GPU which is a bit slower, so it takes slightly bit, otherwise 9 minutes is over quoted. If we were doing it down on the earlier one, then it wouldn't have taken so much of time. Now so that's something which is very much hardware dependent, as I had said in the earlier classes as well. Now if you look down into your accuracy, so you are starting down with an accuracy of something like 59%, which is quite simple. Like in most of these cases, since it was randomly initialized, and your accuracy is technically around 50% is what we have seen with any of these very deep networks over there. What happens is that it closely escalates. So if you look down, so within the first epoch itself, it goes out from 59%, almost 60% to a 74%, a 14% jump. Then it does a 3% jump. Then there is a minus 1% change. So this is where it starts to stagger down a bit and then does it. So one of the major reasons why this happens is that it starts its local oscillations over there, and then since it's not able to get down to the exact minima position, so it's just oscillating around and takes more bit of my time to come down to a convergence. So this is what comes down with my, so my red part is with my training losses over there, my green is with my testing. Now there is something interesting which happens over here as well. Now while my training losses are much lower, my testing loss is obviously higher, and this is pretty much known, but the good thing is that this test curve over there is something which is coming down much faster at a rate. So it means that the generalizability of the model is going up in a better way. Now having said that, we try to look into our accuracy curves over here. Now while the training accuracy is really going high, and a lot of you might tend to think that it's now going close to overfitting, but then the testing accuracy is not something which is going up to that level. So now you need to keep on running it beyond 10 epochs, because 10 epochs is just a very small amount of time in order to keep on continuing this one. Now, now that my training is completely over, the next part which we need to do is that we need to find out what has been the nature of the weights and whether there has been a change of the weights, anything, whatever we had done random initialization versus what comes out at the end of the training process over here. So that we go down and get into my weight initialization and weight visualization part. So these were the weights over here. Now if you remember the first, so let's get back onto the model over here once more. So our first layer for the model was something which had kernel sizes of 7 cross 7, and there were 64 of them, and these were all taking in. So this is my first convolution layer, which took down 3 channel inputs over there, 3 channel which corresponded to an RGB, and it produced out 64 channels. So there were 64 unique kernels present over there, and each of the kernel was of a size 7 cross 7. Okay. Now what came out of from here is that we have 8 cross 8 matrix of 7 cross 7 kernels each over there, and they are all RGB in nature. Okay. So let's get down to visualizing these kernels over here. So these are the nature of these kernels which get learned down over there. Now initially this is the one which is initial before training, so they are all random numbers which are present over there. This is what happens after training, and you would see that the intensity of a lot of these colors have changed, whereas the shade of the color doesn't change. So that practically means that the difference between the RGB over there is not, so the proportionate ratio for RG and B channels are not changing much, but the intensity or the nature of the weights are changing. So let's get into the weight difference over here. So you see a lot of these random patches coming up over here. So there has been significant amount of change around there, but then the proportion in which, so that's the reason why the shades are not changing. And what's really interesting is that you don't fail to, you don't see actually any distinct shape of objects or distinct kernels coming up. Now these are very complex kernels, and they don't have an immediate visual representation. If you are looking down at shallower networks over there, with the shallower network it was much easier to learn down kernels which are very representative of the image. With the more deeper you keep on going, you might not always end up getting down kernels which are very descriptive of how the image properties are, and then that's the nature of these kind of very deep learning systems as they are. Okay. Now the next part over there is if you go back and look into the second convolution layer. The second convolution layer is what takes in yeah, so this is my second convolution layer, which takes in 64 channel input which I have over here, and then I produce 128 channels, and the kernels are of size 1 cross 1. So now what I have over here is just one single matrix value represented. So how we have represented these is that I just take out the first channel out of this 128 channels, and then I display its response over here. So there are total 64 number of kernels. So that's what you see. So each patch over there is just one unit kernel, one channel of that 1 cross 1 kernel, and you have 64 channels. So there are 64 such patches over here. So 1, 2, 3, 4, 5, 6, 7, 8, and you have 8 over here in total. So that makes it complete. So these were the weights which were at the initial part over there, and these are the weights which are there after training, and then you have the difference of the weights coming up over here. Now this difference of the weights is something not much to be intrigued about, and they keep on changing. Now we haven't yet come down to a total convergence, so that's one of the main reasons why these weights are still changing over there, and you don't see a flattened out feature. Now as you can keep on training them for more number of epochs, so we are still at the point of just 10 epochs, and this hasn't yet come down to a saturation. So, typically at your disposal, you can definitely train it down for longer number of epochs, for hundreds of epochs at a stretch, and then keep on doing it out. So, that is something I would leave it down to your side of it. Now, having said that, we have discussed all of this, but in the subsequent lecture we are going to focus more on getting the actual compute complexity analysis done for this one. So, what will be the total number of bytes taken down to actually save the model when it loads out on the RAM, how much of bytes would it require, what will be the total number of floating point computations which will be required over here, as well as and this floating point computation is something which is going to help you decide as to, given a particular hardware which has a certain amount of floating point computations delivery rate, then what will be the total time you would be taking in order to get this delivered out of the system. On top of that, there is also another important point which we will be discussing in the subsequent lecture, and that is on the total operational space complexity. Now, for the operational space complexity, major fact is that if we have larger size kernels, and if there is an intermittent activation response which also keeps on generating. Now, if this is large, then we will take more amount of space, and as a result my batch sizes will have to be reduced. Now, if I do not want to go around with that, then I will have to figure a way of solving it out. So, this is what we will be discussing in the next class, and that is where you will get to know that why in GoogleNet we had smaller batch sizes of 16, whereas over here we can have larger batch sizes of 32, 64 and so on and so forth. So, there is an integrate dependency, but then it is not just dependent on what is the total number of convolution kernels or the number of channels present over there. It is dependent on, also dependent on what will be the total number of activation maps which you are going to produce out. So, this is what we keep on tuned for the next lecture. So, this is the point where we are already done and through with our basic understanding of deep networks. So, in the subsequent weeks we will be understanding more about what is a compute complexity problem within these deep networks, what are my transfer learning issues within these deep networks, and how can we have efficient transfer learning between them, and then subsequently we will get down to even interesting problems, including can we solve out regression problems or convolutional classification called as semantic segmentation problems with these kind of networks. And these, what we have learned till now, are what will be forming down my foundational basics for whatever I am going to do in the subsequent ones. So, that is all what I have to say for today, and then at the end of this week. So, just stay tuned for the subsequent lectures in the next week. Thanks.